Welcome to this calming journey through the universe. Before we begin, if you enjoy relaxing videos that explore deep topics like astronomy, philosophy, psychology, and history, please take a moment to subscribe to the channel and give this video a like. It really helps more than you know, and I'd love to know, where in the world are you listening from, and what time is it right now for you? Drop a comment down below. Whether it's morning, evening, or the middle of the night, I'm grateful you're here. Now, let's begin our peaceful dive into the full story of the universe. When we talk about the universe, we are discussing everything. All of space, time, matter, and energy. It's the most expansive topic we can possibly explore, and yet, it begins in a moment that was almost incomprehensibly small. The story of the universe is not just about stars and galaxies. It's about the birth of time, the transformation of particles, the rise of complexity, and the eventual emergence of life and consciousness, including you, here now, listening to this. Let us begin at the beginning. At the very edge of time itself. The Big Bang. Roughly 13.8 billion years ago, all the energy and matter of the universe was compressed into a single point. Not a point in space, but a point that was space. A singularity. From this incomprehensibly dense and hot state, the universe began to expand. It was not an explosion in space, but rather an expansion of space itself. The Big Bang wasn't loud, it was silent. There was no air to carry sound, only a violent blossoming of energy. In the first fractions of a second, the universe underwent an event known as cosmic inflation. It expanded exponentially, faster than the speed of light. Within less than a trillionth of a second, the universe grew from subatomic size to something the size of a grapefruit, and continued expanding rapidly. During this incredibly brief time, the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces began to separate. At first, they were unified in a single superforce. But as the universe cooled, they split apart, each taking on distinct roles in shaping the cosmos. The energy of this early universe was unimaginably hot, trillions of degrees, and out of this seething energy, particles began to form. The earliest building blocks were quarks and gluons, the components of protons and neutrons. These particles were born in pairs, matter and antimatter, and when they met, they annihilated each other, releasing energy. But for reasons still not fully understood, there was a tiny imbalance. About one extra matter particle for every billion antimatter particles. That small excess of matter is what survived. It's what everything you see is made of. Stars, planets, oceans, trees, your body, and this device you're listening on. As the universe cooled further, quarks combined into protons and neutrons. Within minutes of the Big Bang, these protons and neutrons fused into simple nuclei, mostly hydrogen and helium with trace amounts of lithium. This process is called Big Bang nucleosynthesis, and it was over within the first 3 minutes. But the universe was still a roiling soup of particles. It was hot, dense, and opaque, like the interior of a star. Photons, or particles of light, couldn't travel far without bumping into electrons. This continued for about 380,000 years. Then came a critical moment: recombination. As the universe expanded and cooled, electrons slowed down enough to be captured by nuclei, forming neutral atoms. With electrons now bound into atoms, photons were finally free to travel. This first light is what we see today as the cosmic microwave background, a faint glow that fills the universe, a baby picture of everything. This was the moment the universe became transparent. Light could travel freely, and it has been traveling ever since, filling the cosmos and giving us the clearest window into the ancient past. The next chapter in our story is one of darkness, a time called the cosmic dark ages. After recombination, the universe was filled with hydrogen and helium gas, but there were no stars or galaxies. Space was vast, empty, and growing ever colder. Yet even during this darkness, gravity was at work. Over time, tiny variations in the density of matter, left over from quantum fluctuations in the early universe, began to grow. Clumps of gas slowly gathered together under their own gravity, forming clouds that would eventually collapse into the first stars. But before that light returned, the universe remained dark for hundreds of millions of years. The cosmic dark ages were a silent, shadowy period in the history of the universe. After the brilliant flash of the cosmic microwave background faded, the universe settled into a state of darkness. Hydrogen and helium atoms floated through vast, expanding space. There was no light, no stars, no planets, only gas, drifting in the void. But gravity, the quiet sculptor of the cosmos, was always at work. Within the seemingly uniform sea of hydrogen and helium were tiny ripples, slight variations in density, so small they were imperceptible in the glowing fabric of the cosmic microwave background. But these minute differences, seeded by quantum fluctuations during the inflationary era, would grow into the grandest structures the universe has ever known. Over millions of years, these denser regions pulled in more and more gas. Slowly, imperceptibly, the first clumps of matter began to take shape. Clouds of hydrogen collapsed inward, drawn together by their mutual gravitational attraction. As they collapsed, they grew denser and hotter at their cores. Eventually, the temperature at the center of these clouds became high enough to trigger a process that would forever change the universe: nuclear fusion. The first stars were born. These stars were unlike the ones we see in the night sky today. They were massive, short-lived, and forged from primordial elements. Astronomers call them population 3 stars, the very first generation of stars, composed almost entirely of hydrogen and helium. Because there were no heavier elements, what astronomers call metals, these stars could grow much larger than modern stars, some perhaps hundreds of times the mass of our sun. These giants lived fast and died young, burning through their fuel in just a few million years. And when they died, they did so in spectacular fashion. Supernovae that scattered heavier elements like carbon, oxygen, and iron into the surrounding space. These first supernovae were not just dramatic explosions. They were the universe's first alchemists, transforming simple hydrogen and helium into the ingredients for planets, oceans, and life. With the birth and death of these early stars, the universe began to change. Their light ended the cosmic dark ages, reionizing the surrounding gas and making space transparent again. This era, known as cosmic reionization, was a kind of second dawn, a time when the universe began to glow once more. As more stars formed, they grouped together under gravity, forming galaxies. These were the first islands of light in an endless ocean of darkness. The galaxies that formed in this early universe were small and irregular, but through countless mergers and collisions, they grew into larger and more structured forms. Over billions of years, these mergers would build the enormous spiral and elliptical galaxies we see today, like our own Milky Way. In the vast scaffolding of the cosmos, galaxies gathered into clusters and superclusters, woven together by filaments of dark matter in a web-like structure known as the cosmic web. This vast network stretches across the observable universe, with filaments millions of light years long, threading through immense voids. But while galaxies were forming and stars were shining, there was another, more mysterious force shaping the universe, one that we still don't fully understand: dark matter. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light. We cannot see it directly, but we know it's there because of its gravitational effects. It holds galaxies together, preventing them from flying apart as they spin. It forms the invisible scaffolding upon which the visible universe is built, and dark matter is not alone. In recent decades, astronomers have discovered that even this mysterious substance is dwarfed by an even more enigmatic force: dark energy. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is not slowing down, as once believed. It's speeding up. Something is pushing galaxies apart with increasing speed. This repulsive force, known as dark energy, now appears to make up about 68% of the total energy content of the universe. Together, dark matter and dark energy dominate the cosmos. Ordinary matter, the stars, planets, gas, dust, and everything we can see, accounts for less than 5% of the universe. Think about that. Everything we know, everything we've ever seen, is just a tiny sliver of what's actually out there. And yet, even that tiny fraction has created wonders. In galaxies across the universe, stars continue to form, live out their lives, and die. Some explode as supernovae. Others end as dense neutron stars or black holes. And some, like our sun, live quiet, stable lives, giving rise to something even more remarkable: planets. The formation of planets is the next chapter in our story, and it is a story that brings us much closer to home. As stars formed from collapsing clouds of gas, the leftover material, dust and debris, formed disks around these newborn stars. Within these disks, tiny particles began to stick together, forming larger and larger clumps. Over time, these clumps became planetesimals, then protoplanets, and eventually full-fledged planets. Some became rocky worlds like Earth and Mars. Others grew large and gassy like Jupiter and Saturn. Some systems had dozens of planets. Some had none. Some had planets in tight, fast orbits. Others far and slow. The diversity of planetary systems is staggering, and many of them are still beyond our reach. But in one particular corner of one particular galaxy, a star formed about 4.6 billion years ago. It was a second-generation star, enriched with the heavy elements forged in ancient supernovae. Around it swirled a protoplanetary disk, rich with dust and gas. From that disk, 8 planets emerged, along with countless moons, asteroids, and comets. That star was our sun, and one of those planets was Earth. The story of Earth and the rise of life is not a separate tale. It is a chapter in the story of the universe. Everything on our world, every atom in your body, was forged in the heart of a star billions of years ago. You are literally made of stardust, connected to the cosmos in the most profound way imaginable. In the next part of this journey, we'll follow the formation of the Earth, the appearance of life, and the astonishing path that led from inanimate matter to conscious beings capable of pondering the universe itself. As the sun ignited and began its long, steady fusion of hydrogen into helium, the leftover dust and gas in its surrounding disk gave birth to a family of worlds. Among them was a small, rocky planet, the third one from the star. At first glance, it seemed unremarkable, but this planet would become one of the most extraordinary places in the known universe. That planet is Earth. Around 4.5 billion years ago, Earth formed from the accretion of dust and rock in the protoplanetary disk. These particles collided, fused, and grew, forming a molten, seething ball of rock. During these early stages, Earth was constantly bombarded by asteroids and comets. One of the most dramatic impacts was with a Mars-sized body known as Theia. The collision was so immense that it vaporized a portion of Earth's mantle and flung debris into orbit. That debris eventually coalesced into our moon. This event did more than shape our planet's gravitational partner. It tilted Earth's axis, gave us seasons, and may have even stabilized the planet's rotation. The moon's presence has played a quiet but vital role in making Earth a cradle for life. In its early days, Earth was a violent place. Volcanoes belched gases into the atmosphere. The surface was a chaotic mix of molten rock and cooling crust. The oceans hadn't yet formed, but over time, the planet began to settle. Water, likely delivered by icy comets and outgassed from volcanic activity, collected in low-lying areas. Clouds formed, rain fell, oceans gathered, the surface cooled, a crust hardened, and beneath that crust, the Earth's core remained hot, a churning, iron heart that gave rise to a magnetic field, shielding the planet from solar radiation. Around 4 billion years ago, the first signs of life appeared. We don't know exactly how life began. Scientists have proposed many theories, from deep-sea hydrothermal vents to tidal pools exposed to ultraviolet light to chemical reactions sparked by lightning. Somewhere, somehow, the right molecules came together. Chains of amino acids, nucleotides, and lipids began to self-organize. Membranes enclosed replicating molecules. A simple form of chemistry took its first steps toward biology. The first life on Earth was microscopic, single-celled organisms known as prokaryotes. These early life forms lived in the oceans, feeding on chemicals and sunlight. They were small, but over millions of years, they transformed the planet. One of the most important innovations in the history of life was photosynthesis. Certain bacteria evolved the ability to capture sunlight and use it to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. At first, this oxygen was absorbed by iron in the oceans, forming rust and settling as banded iron formations on the seafloor. But eventually, the oxygen began to build up in the atmosphere. This event, known as the Great Oxygenation Event, happened around 2.4 billion years ago. It was a mass extinction for many anaerobic organisms, but it also opened the door for more complex life. As oxygen accumulated, it enabled the development of aerobic respiration, a much more efficient way of producing energy. This extra energy allowed cells to grow larger and more complex. Eventually, cells began to cooperate. Some cells engulfed others, forming symbiotic relationships. These internalized cells became organelles, specialized structures like mitochondria and chloroplasts. These new, more complex cells are called eukaryotes, and they were the foundation for all multicellular life. Over the next billion years, life slowly diversified. Single-celled organisms gave way to colonies, and colonies evolved into simple multicellular life forms. Algae, sponges, and jellyfish-like creatures filled the oceans. Life remained aquatic, as land was still barren and harsh. Then came a burst of creativity, unlike anything the Earth had seen before. The Cambrian explosion, around 541 million years ago. In a geologic blink of an eye, life exploded into diversity. Organisms developed hard shells, eyes, limbs, and complex body plans. Nearly every major animal group alive today can trace its origins to this period. The oceans teemed with trilobites, mollusks, early arthropods, and jawless fish. Life began to organize into ecosystems. Predator and prey dynamics emerged. The arms race of evolution had begun in earnest. Eventually, life took its first tentative steps onto land. Around 470 million. Years ago, plants began colonizing the coasts. These early plants were small, moss-like organisms. But they paved the way for larger land plants, which transformed the atmosphere and created soil. Insects followed. And then, around 360 million years ago, vertebrates emerged onto land. These were the ancestors of amphibians, reptiles, and mammals. With lungs and limbs, they explored this new environment, adapting to forests, swamps, and rivers. Over millions of years, Earth's surface became a dynamic theater of life. Enormous ferns and forests grew in the Carboniferous period, trapping carbon and creating the coal beds we mine today. reptiles grew larger. Some developed into the ancestors of dinosaurs, which rose to dominance during the Mesozoic era. The age of dinosaurs lasted for over 150 million years. They grew to enormous sizes, ruled every continent, and evolved into a stunning variety of forms. From armored herbivores to flying pterosaurs to swift predators like Velociraptor. But their reign, too, came to an end. Around 66 million years ago, a cataclysmic event struck Earth, likely an asteroid impact near what is now the Yucatan Peninsula in Mexico. The resulting explosion caused massive wildfires, blocked sunlight with dust, and triggered a global extinction. About 75% of all species vanished, including most of the dinosaurs. But not all dinosaurs died. A small group survived. Feathered, winged creatures that we now call birds. With the great reptiles gone, mammals, once small and nocturnal, began to flourish. They diversified into every ecological niche: burrowers, grazers, predators, and eventually primates. In the next part of our story, we'll follow these primates on their extraordinary path, one that leads from the forests of Africa to the moon, the internet, and ultimately to you. The extinction of the dinosaurs was both a tragedy and a turning point. It cleared the stage for a new kind of life to rise, one that had lived in the shadows for millions of years. Mammals. With the dominant reptiles gone, mammals began to evolve rapidly. Freed from predation and competition, they spread into open ecological niches. Some remained small, others became giants. They walked, climbed, swam, and eventually some stood upright. Among them were the primates, an order of mammals that lived in trees, used their hands to grasp, and had large, curious brains. They were social, intelligent, and adaptive. Over time, a branch of primates known as hominins emerged in Africa. The earliest known hominins appeared around 6 to 7 million years ago. They were upright walking, tool-using creatures, not yet human, but on their way. Over millions of years, this lineage produced a variety of species: Australopithecus, Homo habilis, Homo erectus. These early humans mastered fire, crafted tools, and began to migrate out of Africa. Then, around 300,000 years ago, Homo sapiens appeared. Modern humans. At first, they were just another hominin species, living in small groups, hunting and gathering, surviving as best they could. But something changed. Whether it was a genetic mutation, a shift in social structure, or a new way of thinking, Homo sapiens began to behave differently. They painted on cave walls. They buried their dead. They created symbols, language, and culture. They began to remember, to plan, to imagine, and then they spread. Within tens of thousands of years, humans had migrated across the globe, from Africa to Asia, Europe, Australia, and eventually to the Americas. They adapted to frozen tundras and tropical forests, deserts and mountains. They hunted mammoths, built rafts, and formed tribes. With time came agriculture. Around 12,000 years ago, humans began to domesticate plants and animals. This was the Neolithic Revolution, and it changed everything. With farming came settlements. With settlements came surplus. With surplus came trade, social structure, and civilization. The first cities rose in Mesopotamia, in the fertile lands between the Tigris and Euphrates rivers. Others followed in the Indus Valley, Egypt, China, and the Americas. Humans built pyramids and ziggurats, wrote poetry and laws, created gods and governments. They observed the sky and tracked the stars. The first astronomers used stone tools to measure the heavens. They noticed the movements of the planets, the phases of the moon, the return of comets. They began to wonder about the cosmos, just as you do now. From this ancient curiosity, the great questions were born. Where did we come from? What are we made of? What is the universe, and why does it exist? And the answers, as we now know, were written in the light of stars, in the patterns of atoms, and in the echo of the Big Bang itself. The universe had become aware of itself through us. In the next part of this journey, we will explore how humanity's understanding of the universe evolved from myth and observation to science and spaceflight, and how, for the first time, a species reached beyond its own world. As humans gazed upward, the night sky became their first canvas for imagination. Long before telescopes, before writing, before the wheel, our ancestors tracked the stars. They noticed patterns, rhythms, and cycles. The sky wasn't just beautiful, it was a map, a calendar, a clock, and a divine mystery. In every corner of the world, ancient civilizations developed cosmologies, stories of how the universe came to be. In Mesopotamia, people imagined a dome held above the earth by gods. In ancient Egypt, the sky was the goddess Nut, arching over the land. The Greeks filled the heavens with myth. Orion the hunter, Andromeda chained to a rock, Cassiopeia sitting vainly in the sky. But these myths weren't just poetry. They were frameworks for understanding. Early humans used the stars to navigate deserts and oceans, to track the changing seasons, to predict floods and harvests. The cosmos was an eternal rhythm, and we were learning to move in time with it. In ancient China, meticulous records of eclipses and comets were kept. In India, astronomical calculations reached extraordinary precision. The Maya of Central America built observatories aligned with celestial events. The ancient Polynesians used only the stars, currents, and birds to sail thousands of miles across open ocean. One of the earliest attempts to systematize the cosmos came from the Greek philosopher Ptolemy, who lived in Alexandria during the 2nd century CE. His model of the universe placed Earth at the center, with the sun, moon, and planets orbiting in complex loops called epicycles. This geocentric model was elegant and mathematically useful, and it reigned supreme for over 1400 years. But as centuries passed, new thinkers began to question it. In the 16th century, a quiet revolution began. A Polish mathematician and cleric named Nicholas Copernicus proposed something radical. What if the sun, not Earth, was at the center? His heliocentric model simplified the math and offered a new way to understand planetary motion. It was controversial, but it planted a seed. That seed was nurtured by Galileo Galilei, who in 1609 turned a primitive telescope toward the heavens and made astonishing discoveries. He saw mountains on the moon, the phases of Venus, and 4 moons orbiting Jupiter. Clear evidence that not everything revolved around the Earth. For publishing these findings, Galileo faced opposition from powerful institutions. He was tried by the Inquisition and placed under house arrest, but the evidence he uncovered was undeniable, and his work laid the groundwork for modern astronomy. At the same time, another mind was reshaping science itself: Johannes Kepler. Building on the precise data of Tycho Brahe, Kepler formulated his 3 laws of planetary motion, showing that planets moved in ellipses, not perfect circles. This was a breakthrough, a description of the mechanics of the cosmos that matched observation. Then came Isaac Newton, whose universal law of gravitation explained why planets moved as they did. Gravity, he realized, was a force acting across space, pulling objects together. With his laws of motion and calculus, Newton connected the heavens and the earth under a single, elegant framework. The universe, once the realm of myth and mystery, was becoming a place of predictable order. Science had cracked open the sky. As the centuries progressed, the tools of astronomy grew ever more powerful. Telescopes became larger and more precise. Astronomers discovered Uranus, Neptune, and later Pluto. They observed galaxies, nebulae, and star clusters. They measured distances using the flicker of variable stars and the redshift of light. And then, in the early 20th century, a new shift occurred. An astronomer named Edwin Hubble, working with the massive Hooker telescope in California, observed something extraordinary. The light from distant galaxies was stretched, shifted toward the red end of the spectrum. This redshift indicated that those galaxies were moving away from us, and not just some of them, all of them. The farther away a galaxy was, the faster it receded. This discovery transformed our view of the cosmos. It meant the universe was not static, it was expanding. And if it was expanding, then at some point in the distant past, it must have been smaller, denser, hotter. Thus, the idea of the Big Bang was born. Meanwhile, the field of physics was also undergoing its own revolution. In the early 1900s, Albert Einstein proposed his theory of general relativity, which redefined gravity not as a force, but as the curvature of space-time. Massive objects, he said, bend the very fabric of the universe, guiding the motion of everything around them. Einstein's equations predicted phenomena so strange that even he doubted them, like the expansion of the universe or the existence of black holes. And yet time and again, observations would prove him right. Throughout the 20th century, astronomy and physics merged, creating a new discipline: cosmology, the scientific study of the origin, structure, evolution, and fate of the universe. With the launch of space telescopes like Hubble, humanity could peer deeper into the cosmos than ever before. We captured images of distant galaxies, glowing nebulae, and ancient starlight that had traveled for billions of years to reach us. The universe revealed itself as vast beyond comprehension, a place filled with wonder, violence, and beauty, galaxies colliding, stars being born and dying, planets orbiting suns we'd never see with our eyes. In the next part of our journey, we'll explore how humanity began reaching beyond Earth, not just looking at the stars, but traveling into the void between them, the space age and the dawn of interplanetary exploration. By the mid-20th century, humanity had decoded much of the universe's story through mathematics, observation, and relentless curiosity. The stars were no longer unreachable myths. They were places, governed by laws we could understand. Yet, understanding was only the first step. Now, we long to touch the sky. The dream of space travel had existed for centuries. Visionaries like Konstantin Tsiolkovsky, a Russian schoolteacher and mathematician, imagined rockets that could escape Earth's pull. He wrote that Earth is the cradle of humanity, but one cannot live in the cradle forever. His ideas, once considered fantasy, began to take shape with the development of rocketry during the early 20th century. Engineers and scientists across the world were laying the groundwork for what would soon become a new era, the space age. The spark was lit in 1957 when the Soviet Union launched Sputnik, the first artificial satellite, into orbit. It was a small, beeping metal sphere, but its implications were enormous. For the first time, something made by human hands was circling the Earth in space. The launch of Sputnik stunned the world and ignited a race, not just for technological superiority, but for access to the cosmos. The United States soon followed with its own satellites, and in 1961, the Soviet Union made history again. Yuri Gagarin, a 27-year-old cosmonaut, became the first human to orbit the Earth. His spacecraft, Vostok 1, completed a full circuit of the planet in just 108 minutes. He returned a hero, not just to his country, but to all of humanity. For the first time, a member of our species had left Earth, looked back, and seen it whole, a blue marble in a sea of darkness. President John F. Kennedy, recognizing the symbolic and strategic power of space exploration, soon committed the United States to an ambitious goal: to land a man on the moon and return him safely to Earth before the end of the decade. And in 1969, that goal was achieved. On July 20th, Neil Armstrong and Buzz Aldrin, aboard Apollo 11, descended to the lunar surface. Armstrong stepped onto the moon and spoke words heard by millions around the world. That's one small step for a man, one giant leap for mankind. It was more than a technological feat. It was a moment of unity, a demonstration of what humanity could accomplish when it dared to dream and act on that dream. But the moon was just the beginning. The decades that followed saw the launch of interplanetary probes: Voyager, Pioneer, Mariner, and Cassini, each destined for different corners of the solar system. These spacecraft visited every major planet, sending back breathtaking images and invaluable data. Some, like Voyager 1 and 2, even carried messages for other civilizations, etched into golden records, drifting into interstellar space. These missions revealed a solar system of stunning diversity. We saw the swirling storms of Jupiter, the icy rings of Saturn, the tilted blue-green world of Uranus, and the mysterious heart-shaped plains of Pluto. We learned that Venus, though similar in size to Earth, is a hellish world with surface temperatures hot enough to melt lead, that Mars once had flowing water and might have once harbored life, that Europa, a moon of Jupiter, hides a vast ocean beneath its icy shell, and may still harbor life today. Back on Earth, our instruments became more powerful. telescopes orbiting above the atmosphere, like the Hubble Space Telescope, began capturing images of galaxies billions of light years away. We saw the births of stars in stellar nurseries. We watched galaxies collide. We glimpsed the universe as it was when it was young. And yet, the more we saw, the more questions we had. Astronomers discovered that the universe's expansion is accelerating, pushed apart by dark energy, a force we do not yet understand. They found evidence of dark matter, an invisible substance that shapes galaxies and binds the cosmos together. And they began detecting the faint ripples of gravitational waves, confirming Einstein's boldest predictions. Meanwhile, closer to home, a quiet revolution was unfolding. For centuries, we had wondered whether Earth was unique, whether planets like ours existed around other stars. That question was answered with a resounding yes. Thanks to missions like Kepler and TESS, we have now confirmed the existence of thousands of exoplanets, worlds orbiting distant stars. Some are hot gas giants, others are rocky and Earth-sized. A few even lie within the habitable zone, where conditions could allow liquid water to exist. The search for life beyond Earth is no longer speculation. It is a scientific endeavor, driven by data, technology, and an unshakable curiosity. Today, humans live and work in space, aboard the International Space Station, orbiting the Earth every 90 minutes. We are preparing to return to the Moon, and from there, perhaps one day, to Mars. The journey from ancient myths to rocket ships, from firelight to starlight, is a testament to our species' endless drive to explore and understand. In the next chapter, we'll look beyond the planets, into black holes, neutron stars, and the deepest mysteries of the cosmos. The places where time warps, light bends, and the laws of physics are pushed to their limits. As we journey deeper into the cosmos, we move beyond the familiar glow of stars and planets into realms where the rules of physics stretch, bend, and nearly break. This is the territory of neutron stars, black holes, and gravitational waves. The universe at its most extreme. Let's begin with neutron stars. When a massive star, much larger than our Sun, reaches the end of its life, it undergoes a final, spectacular death. As its nuclear fuel runs out, it can no longer hold itself up against gravity. The outer layers collapse inward and rebound in a cataclysmic explosion known as a supernova. What's left behind depends on the original star's mass. If the core that remains is between about 1.4 and 3 times the mass of our Sun, it collapses into a neutron star. Imagine an object more massive than the Sun compressed into a sphere only about 20 kilometers across, the size of a city. This is a neutron star, unimaginably dense, with gravity so intense it warps the very fabric of space. A single teaspoon of neutron star material would weigh around 1 billion tons. The core is made almost entirely of neutrons, packed so tightly that atoms can't exist in their normal form. These stars spin rapidly, sometimes hundreds of times per second. and their magnetic fields can be trillions of times stronger than Earth's. Some neutron stars become pulsars, cosmic lighthouses that beam radio waves from their poles. As they spin, these beams sweep across the sky, creating pulses that we can detect on Earth with astonishing regularity. These pulses are so precise that some pulsars rival atomic clocks in their accuracy. But for even more massive stars, something stranger happens. If the core left after a supernova exceeds a certain threshold, gravity wins completely. Nothing can stop the collapse. The matter is crushed down into a point of infinite density, a singularity, and a black hole is born. Black holes are not simply holes. They are regions of space where gravity is so strong that nothing, not even light, can escape. The boundary around this region is called the event horizon. Once something crosses this boundary, it's gone, lost to the observable universe. Despite their name, black holes are not entirely black. Thanks to the groundbreaking work of physicist Stephen Hawking, we know that black holes can emit a faint radiation, now called Hawking radiation, and may eventually evaporate over immense timescales. Black holes come in many sizes. Stellar mass black holes form from dying stars. But at the centers of most galaxies, including our own, lie supermassive black holes, with masses millions or even billions of times greater than the Sun. The one at the center of the Milky Way is called Sagittarius A. For years, we inferred black holes only by their effects, how they tugged on stars and bent light. But in 2019, astronomers achieved a monumental breakthrough. Using a global array of radio telescopes, they captured the first image of a black hole's event horizon, a glowing ring around a dark shadow 55 million light-years away in the galaxy M87. It was a triumph of science, collaboration, and technology, a photograph of the unseeable. Yet even black holes do not exist in isolation. They sometimes form binaries, pairs that orbit one another, spiraling ever closer over time. As they merge, they send ripples through the fabric of space-time itself, gravitational waves. Predicted by Einstein over a century ago, gravitational waves were detected for the first time in 2015 by the LIGO Observatory. These waves stretch and compress space as they pass through, carrying information about the most violent events in the universe: colliding black holes, neutron star mergers, even echoes from the early universe. This detection opened a new window into astronomy, one not of light, but of movement. Now we can listen to the universe, feeling its tremors through the very structure of reality. These discoveries raise profound questions. What happens at the singularity, the center of a black hole? Can information be truly lost, or is there a deeper law that preserves it? Could black holes connect to other places in space, or other universes? The answers remain elusive. Black holes sit at the crossroads of two great theories: general relativity, which describes gravity and space-time, and quantum mechanics, which governs the behavior of particles. But these two theories are fundamentally incompatible. Reconciling them, uniting gravity with quantum physics, is one of the greatest unsolved challenges in science. Physicists have proposed many ideas: string theory, loop quantum gravity, holographic principles, and more. But so far, no single theory has been confirmed. The universe at its smallest and its largest scales still holds secrets that we cannot yet reach. And yet, even in our uncertainty, we are learning. In the darkness of black holes, in the faint ripples of gravitational waves, in the whispers of ancient photons, we are uncovering the hidden structure of the cosmos. And all of this, all of it, from atoms to galaxies, from stars to minds, emerges from the same simple beginnings. From quantum fluctuations in the infant universe to superclusters of galaxies, everything is part of a single, unfolding story. In the next part, we'll turn our attention to time, what it is, how it flows, and how the universe may one day end. Time, the invisible river in which we all move. We are born into it, carried by it, and ultimately return to it. But what is time, really? In our everyday experience, time feels like a constant. Seconds tick by, minutes pass, days turn into years. But in the grand scheme of the universe, time is far from absolute. Isaac Newton imagined time as a uniform backdrop, an invisible stage upon which events unfold. But Albert Einstein shattered that view with his theories of relativity. According to relativity, time is not separate from space. It is part of a four-dimensional fabric called space-time, and it is shaped by mass and motion. The stronger the gravity, or the faster you move, the slower time passes. A phenomenon called time dilation. This isn't just theoretical. It's been confirmed with atomic clocks, on airplanes, satellites, and in high-speed particles. Astronauts aboard the International Space Station age a tiny bit slower than people on Earth. GPS systems even correct for the time dilation caused by Earth's gravity, or they'd quickly become inaccurate. This means that time is not universal. Each of us experiences our own version of it, depending on where we are and how we move. But why does time seem to flow in only one direction? Physicists call this the arrow of time. In theory, the fundamental laws of physics are reversible, meaning that, mathematically, time could run forward or backward. But in reality, we experience only forward motion. Memories accumulate, entropy increases, and broken eggs do not spontaneously reassemble. This arrow of time is tied to the concept of entropy, a measure of disorder. The second law of thermodynamics states that in a closed system, entropy tends to increase. From a highly ordered state, like the early universe, the cosmos evolves toward disorder, and this trend gives time its direction. The universe began in a low entropy state. As it expands, stars form, burn, and die. Planets cool, galaxies spread apart. Complexity gives way to simplicity. Over trillions of years, if the trend continues, everything will move toward thermodynamic equilibrium, a state of maximum entropy, sometimes called heat death. In this scenario, stars burn out, matter decays, black holes evaporate. The universe becomes cold, dark, and empty, a vast sea of nothingness, with no energy gradients, no structure, and no memory of what once was. But this is just one possibility. Another is the Big Crunch. If the expansion of the universe were to reverse, gravity could pull everything back together. Galaxies would converge. Temperatures would rise. The cosmos might collapse into a singularity, potentially to rebound again in a big bounce. A third possibility is the Big Rip. If dark energy continues to accelerate the expansion, its effect might grow stronger over time. Eventually, galaxies, stars, planets, and even atoms could be torn apart, shredded by the fabric of space itself. Each of these outcomes depends on the true nature of dark energy, a force we barely understand. Is it constant, like Einstein's cosmological constant? Is it dynamic, changing over time? Could it eventually reverse or vanish? These are questions we cannot yet answer. But even as we ponder the end, we must also recognize that we are living in a special moment. A universe rich with structure, filled with stars, and home to life. We are here, conscious, thinking, in a universe that has existed for 13.8 billion years and may continue for trillions more. That we exist at all, in this fleeting sliver of cosmic time, is both a miracle and a mystery. And in this moment, we can study the stars, reflect on our place in the cosmos, and wonder what comes next. In the next part, we'll look closer to home, at our solar system, its strange and varied worlds, and how it came to be a cradle for life. Our solar system, a small, radiant corner of the galaxy, is our home in the vast expanse of space. It is the place where the story of Earth and humanity unfolds, but it is also filled with strange worlds, ancient relics, and unsolved mysteries. The story begins about 4.6 billion years ago, when a cloud of gas and dust, the remnants of earlier generations of stars, began to collapse under its own gravity. At the center, material gathered into a hot, dense core that would ignite to become our sun. Around this infant star, a protoplanetary disk of gas, ice, and dust spun into motion. Within this swirling disk, particles collided and stuck together, forming ever larger bodies. Over time, these clumps grew into planetesimals, then protoplanets, and finally, the planets we know today. The innermost planets, Mercury, Venus, Earth, and Mars, are small, rocky, and dense. These terrestrial planets formed close to the Sun, where heat drove away lighter gases, leaving behind metals and silicates. Farther out, beyond the frost line, it was cold enough for ice to condense. Here, larger planets formed, sweeping up hydrogen and helium to become the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. Beyond Neptune lies a realm of icy bodies, the Kuiper Belt, home to Pluto and many other dwarf planets. And farther still, a distant shell of frozen objects called the Oort cloud marks the outer boundary of the solar system, extending almost a light year from the Sun. Each of these worlds is unique. Mercury, the smallest planet, is a scorched world of craters and cliffs. with temperatures that swing from freezing to blistering. It orbits closest to the Sun and has no atmosphere to speak of, just a silent, baked landscape. Venus is Earth's twin in size, but not in nature. Shrouded in thick clouds of sulfuric acid, its surface is a hellscape of 900-degree heat and crushing pressure. The greenhouse effect on Venus is runaway and absolute, a warning, perhaps, of climate tipping points closer to home. Earth, of course, is the jewel, the only known world where life thrives. It is a planet of oceans and continents, storms and seasons, forests and deserts. A place of blue skies, liquid water, and a delicate balance that sustains complexity. Mars is a world of red dust, extinct volcanoes, and ancient riverbeds. It once had a thicker atmosphere and flowing water. Today it's cold and dry, but tantalizing evidence suggests it might once have supported microbial life and could still harbor it beneath the surface. Beyond the asteroid belt lies Jupiter, the largest planet, a gas giant so massive it could contain all the other planets combined. Its atmosphere is striped with powerful storms, including the Great Red Spot, a cyclone twice the size of Earth that has raged for centuries. Jupiter's immense gravity shapes the solar system. It deflects asteroids, influences orbits, and shepherds a retinue of more than 90 moons, some of which are worlds in their own right. One of them, Europa, is covered in ice, but believed to have a subsurface ocean. Its salty depths, warmed by tidal forces, may harbor the conditions for life. Saturn, the second gas giant, is famous for its rings, a brilliant system of ice and rock particles that orbit in graceful bands. Saturn also has an impressive family of moons, including Titan, which has rivers and lakes of methane and a thick orange atmosphere. Uranus, tilted so far it essentially rolls on its side, is an ice giant with a pale blue hue. It spins oddly and has rings of its own, though they are faint and dark. Neptune, the farthest known planet, is deep blue and stormy. Winds on Neptune reach the highest speeds in the solar system, up to 1,200 miles per hour. It has moons as well, including Triton, which orbits backward and may be a captured object from the Kuiper Belt. Then there's Pluto, once the 9th planet, now classified as a dwarf planet. Though small, Pluto is geologically active. It has icy plains, nitrogen glaciers, and towering ice mountains. In 2015, NASA's New Horizons spacecraft flew past Pluto, revealing a world far more complex than anyone expected. Our solar system also teems with smaller objects, asteroids, comets, and meteoroids. These are the leftover building blocks of planets, ancient relics from the birth of the sun. Comets, in particular, are time capsules. When they approach the sun, they sprout bright tails of gas and dust, illuminated by sunlight. Some may have delivered water and organic compounds to early Earth, seeding the ingredients for life. And of course, we must not forget the sun, the heart of it all. The sun is a G-type main sequence star, converting hydrogen into helium through nuclear fusion. Every second, it releases more energy than humanity has ever produced. Its light travels for 8 minutes across space to reach us, illuminating our skies, driving our weather, and sustaining our ecosystems. The sun is about halfway through its life. In another 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, and possibly Earth. Eventually, it will shed its outer layers and shrink into a white dwarf, a dense, cooling remnant that will fade over time. The solar system, like all things, is impermanent, but for now, it is our cradle, our laboratory, our home. In the next part of our journey, we'll zoom back out, not just to observe the universe, but to reflect on what it means to be observers. We'll explore the rise of human thought, the philosophy of existence, and the cosmic significance of consciousness. The universe is vast, ancient, and indifferent, a place where stars are born and die, where galaxies drift for billions of years, and where black holes swallow light itself. And yet, somehow, in at least one corner of this immense cosmos, the universe became aware of itself. That corner is the human mind. How extraordinary it is that stardust, forged in the hearts of ancient suns, could eventually give rise to thought, memory, language, and dreams. We often think of the universe as something out there, beyond us. But we are not separate from it. We are in the universe, and the universe is in us. The atoms that make up your bones, your heart, your brain, they were born in stars that died billions of years ago. In that sense, consciousness is the universe observing itself. A brief, flickering light in the dark, and yet one capable of wonder. From early humans gazing at the stars, to modern scientists decoding the secrets of space-time, our species has always sought to understand. That impulse, the desire to know, to explore, is not just a trait. It's our defining quality, and it raises deep questions. Why is there something rather than nothing? Why does the universe follow laws we can understand? What is the origin of consciousness? What is our role in this immense unfolding of space and time? These are questions that science alone cannot fully answer. They touch on philosophy, spirituality, and meaning, dimensions of thought that have guided human reflection for millennia. Ancient thinkers looked to the stars and saw divine order. They imagined gods and creators, celestial spheres and purposeful design. In many traditions, the cosmos was seen as a mirror of the soul, a living, breathing whole. The Greek philosophers pondered the nature of existence. Plato imagined a world of perfect forms, beyond the physical. Aristotle sought a prime mover, an uncaused cause that set everything in motion. In the East, Hindu cosmology envisioned an infinite cycle of creation and destruction, with a timeless reality beyond appearances. Buddhist philosophy emphasized impermanence, that all things arise and pass away, and saw consciousness as part of a vast interdependent flow. Christian and Islamic theologians merged spiritual insight with natural philosophy, seeking to understand God's creation through the study of nature. Many early scientists, like Newton, Kepler, and Galileo, saw their work as uncovering the divine order of the cosmos. In modern times, science has uncovered profound truths. the age of the universe, the laws of motion, the structure of DNA, and yet, the deeper we look, the more mysterious things become. What is consciousness? Is it merely the product of neurons firing in the brain, or something more? Some philosophers argue that consciousness is emergent, a result of complexity, that when matter becomes sufficiently organized, awareness arises. Others believe consciousness may be fundamental, a basic feature of reality, like space or time. Still others ask whether our perception of reality is a simulation, a mental model constructed by the brain to make sense of limited sensory input. After all, what we see and feel are interpretations, filtered through evolution and experience. And yet, we do experience. We know, we reflect, we ask. This alone makes us special. In the cosmic scale, we are tiny, smaller than grains of sand on an endless beach. But in another sense, we are vast. We hold galaxies in our minds. We compress billions of years into stories. We imagine futures that have not yet come to pass. We are creatures of both fact and fiction, of data and dreams. And in our brief lives, we create meaning through art, love, science, poetry, compassion, and curiosity. We build telescopes to look out and build relationships to look in. We reach for the stars, not just with rockets, but with wonder. Some thinkers believe that meaning is something we impose on a silent universe, that there is no inherent purpose, only the meaning we create. Others believe that the universe has intrinsic value, that life is part of a larger plan or destiny. Wherever you fall on that spectrum, one thing remains true. Our existence is precious, fragile, rare. So far as we know, Earth is the only place in the universe where life exists. The only place where matter has come alive, where molecules have begun to speak, sing, and seek. But could there be others? In the next part of our journey, we'll explore the possibility of life beyond Earth, alien civilizations, the search for signals, and the questions that follow. If the universe is so vast, where is everyone? As we reflect on the nature of consciousness and our place in the universe, we inevitably confront another great mystery: mortality. We are temporary beings, born into a world we did not choose and destined to leave it one day. This realization can be overwhelming, but it also gives shape to our lives, urgency to our days, and depth to our choices. In the face of an indifferent cosmos, we create stories, narratives that help us make sense of existence, stories of beginnings and endings, of gods and galaxies, of heroes and homes. These stories don't just entertain us, they give us identity, continuity, and hope. And perhaps that is one of the most important functions of intelligence in the universe: to tell stories, to take the chaos of reality and thread it into something meaningful. From cave paintings and oral myths to science fiction and space exploration, we've always used narrative to reach beyond ourselves. Even this journey, the one you're hearing now, is a story. A way to gather 13.8 billion years of cosmic evolution into a tale that you can carry with you, quietly, as you fall asleep. But meaning isn't only found in grand questions or epic scales. It's in the small things, too. The way sunlight falls through leaves, the quiet of early morning, the laughter of someone you love. These moments may not change the cosmos, but they change us. Some philosophers and scientists have proposed that intelligence, particularly reflective, self-aware intelligence, might serve a deeper purpose in the cosmos, that perhaps through life, the universe is able to understand itself. Think of it this way: without observers, without minds to ask questions, the universe is simply a vast machinery of atoms and voids. But with consciousness, it gains a mirror, a way to perceive itself. Carl Sagan once wrote, "We are a way for the cosmos to know itself." And maybe that's not just poetic. Maybe it's literal. Maybe intelligence is not an accident, but a phase transition, a flowering of complexity with profound significance. If so, then every act of learning, of wonder, of kindness becomes a sacred thread in the cosmic tapestry. Even sleep, this gentle surrender to the unconscious, is part of that rhythm. A cycle of restoration that echoes the cycles of stars, seasons, and tides. As you drift deeper into rest, think of this. You are made of matter that has existed since the beginning. Every cell in your body carries atoms from stars that lived and died long before Earth was born. Your breath contains molecules that once traveled through the lungs of trees and oceans of ancient planets. You are not separate from the universe. You are of it. And even in your silence, your stillness, you are part of its ongoing story. In the next part, we'll explore one of the most compelling questions of all. Is there life beyond Earth? Are we alone in the universe, or part of a vast, hidden network of minds? For most of human history, the night sky was a mystery, beautiful, distant, and silent. But as we began to understand the universe, a question emerged, both exhilarating and haunting. Are we alone? The universe is vast, incomprehensibly so. Our galaxy alone contains around 400 billion stars, and there are estimated to be 2 trillion galaxies in the observable universe. Around many of those stars are planets, exoplanets, some of which may be Earth-like, with liquid water, stable climates, and the ingredients for life. Given these numbers, many scientists believe that life must exist elsewhere, and not just microbial life, but perhaps intelligent civilizations, species that build, think, and wonder, like us. This possibility is not just science fiction. It is now a major scientific field. Astrobiology, the study of life in the universe. Let's start close to home. On Mars, dry riverbeds, ancient lake basins, and recurring slope lines suggest that water once flowed across its surface. Today it's a cold desert, but beneath the surface, liquid water may still exist. Robotic missions like Perseverance are searching for signs of past microbial life, preserved in the Martian rocks. On Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, scientists believe vast oceans exist beneath icy crusts. These oceans are heated by gravitational tidal forces, a source of energy that could allow life to thrive, even in the absence of sunlight. These are not guesses. NASA has observed plumes of water vapor erupting from Enceladus and believes similar processes occur on Europa. Future missions are being designed to probe these oceans, to search for organic molecules, or perhaps something more. Elsewhere, the search continues with telescopes like Kepler and TESS, which have identified thousands of exoplanets. Some of these lie within the habitable zone, not too hot, not too cold, where liquid water might exist. We study these planets' atmospheres, looking for chemical signatures, biosignatures, such as oxygen, methane, and carbon dioxide in ratios that suggest life. But life doesn't always mean intelligence. The search for intelligent life, SETI, the search for extraterrestrial intelligence, focuses on detecting technosignatures, radio waves, laser pulses, or other artificial signals from distant civilizations. For decades, radio telescopes have scanned the sky, listening for patterns that nature wouldn't make. In 1977, a powerful narrowband radio signal was detected from the constellation Sagittarius. It lasted just 72 seconds and was never repeated. It became known as the WOW signal. Intriguing, but inconclusive. Despite the silence, many scientists remain optimistic. Given the age of the galaxy, intelligent civilizations could have arisen billions of years before us. They might be using technologies beyond our understanding, or they might choose not to communicate. This is the heart of the Fermi paradox, named after physicist Enrico Fermi, who asked, "If intelligent life is common, where is everybody?" Many solutions have been proposed. Perhaps intelligent life is rare or short-lived. Perhaps civilizations tend to self-destruct before achieving interstellar travel. Perhaps they are watching silently, practicing non-interference. Or perhaps they are using forms of communication we haven't yet discovered or cannot yet detect. There's also the possibility that we are the first, that in the vast darkness, Earth is the spark of awareness that will one day light other stars. Or we may simply be isolated by distance and time. The universe is so vast and light travels at a finite speed. Even if signals are out there, they may take thousands or millions of years to arrive, or may have passed by before we were listening. Still, the search continues. Projects like Breakthrough Listen are scanning the skies with unmatched sensitivity. Upcoming missions and telescopes like the James Webb Space Telescope may detect atmospheric signatures on distant planets. Some scientists are even considering sending messages, broadcasting Earth's presence to the cosmos. But should we? Some argue that announcing ourselves could be dangerous, that we might attract the attention of civilizations not unlike us in curiosity, but different in intention. Others believe that reaching out is our destiny, that intelligent life, once aware, seeks to connect. Whatever the truth, the search itself is a noble endeavor. It tells us something profound about who we are, that even in our solitude, we hope. We imagine others looking up at their own skies, wondering the same thing. We are not just watchers of the stars. We are listeners, dreamers, and senders of signals. And maybe, someday, the silence will break. In the final part of our journey, we'll return to Earth, to the future of our planet, our species, and our role in the unfolding story of the universe. And now, we return home. After traveling across billions of years and countless light years, through stars and atoms, through galaxies and black holes, we find ourselves once again on Earth, a small, fragile world orbiting an average star, in the suburbs of a galaxy among trillions. And yet, this world is anything but ordinary. It is here that life arose, evolved, and became aware. It is here that the universe began to ask questions about itself, and it is here that the future will unfold, shaped by the choices of a species still in its early adolescence, us. What comes next? The 21st century and the centuries that follow may determine whether humanity survives, thrives, or fades into the background of cosmic history. We face great challenges: climate change, biodiversity loss, resource depletion, nuclear risk, and the unknown perils of artificial intelligence and biotechnology. These are not just technical problems. They are tests of wisdom, compassion, and cooperation. But we also have extraordinary tools, knowledge, creativity, and an expanding awareness of our place in the universe. We are not helpless. We are builders. The path forward may include sustainable technologies, interplanetary travel, and global collaboration on a scale never before seen. We may colonize Mars. We may build space habitats. We may explore the moons of Jupiter and Saturn, sending machines and eventually people to the outer solar system. We might even go beyond. One day, our descendants could send probes to other stars, powered by solar sails, nuclear drives, or technologies we have not yet imagined. They could establish outposts in distant systems, spreading life across the galaxy. If humanity survives long enough, we may become a Type 1 civilization on the Kardashev scale, mastering the energy of our planet. Then Type 2, harnessing the power of our star. And perhaps, one day, Type 3, commanding the energy of an entire galaxy. These are dreams, bold, speculative, and far away, but they are not impossible. And even if we never leave Earth, there is still so much to do, so many ways to deepen our understanding, care for each other, and live with greater purpose. The most important journey may not be to the stars, but within, to grow wiser, kinder, more connected, to see ourselves not as isolated individuals or nations, but as parts of a living planet, floating in darkness, held together by gravity, light, and shared destiny. Carl Sagan, reflecting on a photograph of Earth taken from 4 billion miles away, wrote of the pale blue dot, our home, barely a pixel suspended in a sunbeam. He reminded us that every saint and sinner in the history of our species lived out their lives on that dot, and he urged us to be kind to one another and to cherish the only world we've ever known. Perhaps, in the end, that's what the universe asks of us. Not just to explore and to understand, but to care, to protect the spark of consciousness, to nurture life, and to become the stewards of a future still unwritten. The story of the universe is vast, and our chapter in it is brief. But it is ours. So as you close your eyes tonight, let your thoughts drift not just to the stars, but to the stories we tell, the ones that make us human and the ones we've yet to write. You are part of a grand and beautiful unfolding. You are stardust that dreams. Sleep well, traveler.